Hello, my name is Sangyoon Kim.
And my name is Tiancheng Jiang.
This video is about to introduce single setup processor that we've done for ENGF0001 Challenge 1. My name is Sangyoon Kim, and a single cycle processor that we've built is able to carry out a number of functions, including long words, stored words, branch, R-type instructions, and jump. For long words, we have the register file, taking the instructions from the ROM. The sign extends takes the last 16 digits, which is the IMM value, from the instructions. The multiplexer here takes the value of the output from the sign extend. The output RD1 of the register file and the output of sign extend goes to the ALU, while the ALU is set to the addition 010, and the result goes to the memory. The data in the memory is then written back to the register file, and the address of the next instruction is determined so that the next instruction can be carried out. For store words, we have the register file taking the instructions from the ROM. Yeah, and this is the register file. The sign extend takes the last 16 digits, which is IMM value from the instructions. The multiplexer here takes the value of the output from the sign extend. While the ALU is set to the addition, the output of RD1 and the output of sign extends goes to the ALU, and the results goes to the memory. For store words, 20 to 16 digits from the instructions go to A2 in the register file, and then is written to the data memory. After that, the address of the next instruction is determined so that next instructions can be carried out. For R-type instructions, the data from RD2 of register file is sent to the multiplexer and is further sent to ALU. Then the result from ALU goes to this multiplexer as value is set to 0. Then the value from this multiplexer is sent to WD3 of the register file. And then 10 to 16 digits memory and the 15 to 11 digit memory are sent to 5-bit multiplexer from the instruction. And then they are further sent to A3 of register file. When jump function is enabled, the left sheet over here takes the last 26 digits from the instruction memory and output a 28 digit bus. This bus joined with 31 to 28 digits, they join in here, and the 31 to 28 digits from the result of the adder over here. This generates 31 digit bus, which goes into the multiplexer over here, whose S input is determined by jump function. The output of this multiplexer goes back into the instruction memory to determine the next instruction.
So this is Tiancheng, and I will be talking about the branch function our single cycle processor has. The branch function is a kind of an I-type function, and by I-type function, the whole instruction is divided into 4 parts. The first 6 digits from the 31st to the 26th digit is the OP code, and then the 25th digit to the 21st digit is the RS. The 20th digit to the 16th digit is the RT, and then the last 16 digits is the IMM. If the OP code is set to 000100, that means the branch function is activated, and in the control unit, the branch output is set to 1. Meanwhile, in the register, the input of A1 and A2 respectively takes the value of RS and RT, and then the output of the register file goes to the ALU. One of the output has to go through the multiplexer because in the case of longword and stalwart, the second input of the ALU has to go from the sonic stand, so a multiplexer has to be used here to determine in which situation what kind of an input is taken. In this case, the ALU SRC is set to 0, so the output from the register file is taken into the input of the ALU. In this case, the ALU control is set to 110, which means the ALU is doing the subtraction, and the output of the ALU goes into a component over here, which check whether all of the output is equal to 0. So if the output is all the output is 0, that means the value of RD1 and RD2 is the same, which means the address is the same. So the output is 1. Otherwise, the output is 0. And when the output is 1, this AND function and the output from this component and the branch together. And since the branch is 1, the output of this AND function depends on the output from this component. So if the output of this component is 1, then the output of this AND function is 1. Thus, the multiplexer over here is 1. Otherwise, the multiplexer here is 0. That means if the two addresses is the same, the S inputs of this multiplexer is 1. Otherwise, it's the 0. When the multiplexer is 0, which means that the two addresses are not the same, then it takes the value from the 32-digit adder, which at the current instruction address was 4, which is a normal kind of a determination of the next instruction to go straight to the instruction that is right after the current one. However, if the two addresses are the same, the S inputs of this multiplexer turns into 1, which takes the output from this adder over here. This adder adds the value of the left shift with the value from over here. The current instruction address was 4. The left shift takes the output from the sonic stand, which is the IMM value, which is the target address value, which represents the target address value. So if this multiplexer takes the S inputs of this multiplexer is set to 1, the address is equal to each other, the branch function can automatically jump to another targeted instruction address that we wanted to jump to. So that about sums up the composition of the top level entity of the processor. And now let me talk about the program that are stored in the ROM, which are also the instructions that are stored in the ROM. So the first program is the decimal counter. It's pretty straightforward. So the aim is to let the FPGA show the numbers from 0 to 9, and if it reaches 9, and then it will be reset to 0 and start all over again. So regarding this part of the program over here, we have the initialization part of the program that sets T1 to 0 and T2 to 9. And then in the loop part of the program, we show the value of T1 onto the FPGA board. After we show this value, we check whether the value of T1 has reached 9. If it has, then the program will carrying out the reset part of the program, and if it isn't, it will continue on carrying out these two lines of the program, which is to add the value of T1 by 1 and then jump back to the start of the loop part of the program. If the value of T1 has reached 9, it will jump to the reset part of the program, and the value of T1 will be reset to 0, and after the value is being reset, it will jump back to the start of the loop part of the program again. And this part of the program is the part to display all the squared numbers on our FPGA board. There's an interesting feature regarding the squared numbers is that the difference between the two neighboring squared numbers is increased by 2 every step. So for example, the first squared numbers is 0 and the second one is 1, and the difference between them is 1. And then the second and third squared numbers, the 1 and 4, the difference is 3. And then between 4 and 9, the difference is 5. So the difference will be increased by 2 every time, 1, 3, 5, and onwards. So basically, that is the mindset of the part of the program that displays the squared numbers. So in the part of the initialization, the T1 will be initially set to 0. That's the first squared number. The value of the first squared numbers is 0, and the value of T2, which is supposed to be the difference between two squared numbers, so that it can be added to T1, is set to 1. And during the loop part of the program, the loop part of the program was first display the value of T1 to the FPGA board, and after the value is displayed, the value of T2 will be added to the value of T1 so then the T1 can store the next square number, and after the next square numbers, the value of the next square number is stored, the value of T2 is increased by 2, and then jump back to loop to carry out these procedures all over again, so that all of the squared numbers can be displayed on the FPGA board one at a time, and it goes bigger and bigger. So the third program that we did was to show the numbers that are the power of 2s onto the FPGA board. So in decimal numbers, they are 1, 2, 4, 8, 16, 32, 64, 128, and so on. In hexadecimal form, they are 1, 2, 4, 8, and then 1, 0, 2, 0, 4, 0, and etc. This program is pretty straightforward. You just have to double the value every step. So we start with the initialization process to initialize the T1 to 1. And then we start the looping process. We first show the value of T1 to the FPGA board, and then we add the value T1 to the value T1, which basically just doubles the value of T1 every step, and jump back to the start of the looping of the program.